Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. Today we are going to finish this chapter on Spark, and then if time permits, we are going to start studying document stores, and I will also motivate, of course, why we need to do this. I will ask you a question on Clicker as I usually do, and then a quick reminder on what we've covered so far, and then we'll continue mostly with data frames, which is the last part that we've been missing. All right. So you remember for MapReduce and for Spark that we have tasks and we have slots, and we discussed the number of tasks that there should be versus the number of slots that we have available. And so the question is, if you have a naive approach and you assign one task per slot, you have, for example, 1,000 slots and you schedule 1,000 tasks, what is the issue with this? Why do we not want to assign one task per slot? Why do we want more tasks per slot or less? It's a bit of time to wake up in the morning. Okay, let's start looking whether there's a majority somewhere. Yes, there is a majority. And, you know, the majority is not always correct. But in this case, it is, in fact, correct. Indeed, this is exactly what happens. The slots, if they have each one task, might take more or less time to complete each task. It's like with the postcards that we saw the other day as an example, filling the postcards while on vacation. Some slots are going to be faster and some slots are going to be slower. And those that are faster will just be idle without doing anything. And everybody is waiting for the slots that take more time to complete their tasks. So if you have more tasks, if you have like five times as many tasks as slots, like 1,000 slots and 5,000 tasks, then you spread it a little bit more. And those that are finished a bit earlier will complete more tasks. And those that finish a bit later will complete less tasks, right? So you basically spread a little bit the risk that you have regarding the time that it takes. All right. Let me get back to the slides then. Okay, so where were we? We saw that in MapReduce, there's just a map and a reduce phase, right? You start with a collection of key value pairs, then you have the map phase, you shuffle around, then you have the reduce phase, and then you output a collection of key value pairs. We saw that Spark is more generic because first you can have collections of whatever, doesn't need to be key value pairs, collection of anything you'd like. The second generalization is that instead of a simple two-phase process, we can have a fully general DAG, directly the cyclic graph, that looks like this, just cannot have any cycles, and also called a dependency graph. And every node in there, that it's a data set, an intermediate data set, that's called an RDD, for resilient distributed data set. And these are collections of whatever. All right, and as you might remember, it's lazy, meaning that for the moment, nothing happens. It's only when you request the contents of one of the RDDs that it's automatically triggering the computations of all the transitive closure, the reverse transitive closure in the past. Okay, this is a reminder of how it looks like when you use it either in a Python notebook or on the command line. Where you have all this huge restaurant menu of transformations and actions and the methods that you can use to create new RDDs. And that's a simple example with a flat map and a count by value. We also looked at the physical level. This is all what's hidden from the user, but what makes it magically fast. And we saw that there is an optimization that we can do, because when the transformations that turn RDDs into other RDDs, when these transformations do not have any spaghetti, in the sense that the dependencies are narrow, remember, like filtering, like mapping, like flat map, and so on. So when there is no spaghetti, there is no shuffling needed, and then you can simply merge them into a single stage. And as a result, when you distribute all the computations, you can directly call the functions over multiple transformations. For example, the blue, orange, and green that you see here, that might be a flat map followed by a filter, but that you do for every single value in your input in a single go. So the one in the middle gets thrown away immediately, right? So it means the RDD that you would have in the middle never even gets materialized anywhere. It's just intermediate results. You directly get the RDD after the second transformation. And then you spread it all over your cluster, right? Every core is basically a slot. A slot processes a sequence of tasks, and a task consists in repeated calls to the chain of transformation functions that turn an input value into an output value. Who is with me? Okay, so that's what we covered already in the previous weeks, right? And so this is where we left, where this basically can be done every time there's no spaghetti. But of course, sometimes there is a bit of spaghetti whenever you group, whenever you sort. And in that case, you need to change the stage. So this is called a stage, right, when it's grouped together. And whenever there's a shuffling, you need to go to another stage, right? And there are ways to avoid some of the shuffling, because shuffling is very expensive. And the way you avoid it is, do I have it here? No, let me shift around. You basically can optimize. If you already pre-partition the input data, for example, if it's already stored on disk in a sorted fashion, then the data is already partitioned. And if the way you partition is compatible with the way you shuffle, meaning that the data is already organized in buckets that correspond to where you want them after the shuffling, then you can just skip completely the shuffling for that, right? Who agrees with that? If the data is already organized in partitions, for example, you want to sort the data, it's already sorted, you don't need to do it again. Imagine you want to group the data. For example, you want to group the data based, I don't know, on birth dates. Imagine the data is already sorted by birth dates and organized that way across the cluster. Then you don't need to shuffle, because the data is already, the data that has the same birth date is already collocated on the cluster, right? So in these cases, you can avoid the shuffling. So this is why here you have these two straight lines from the right side, where you don't need to shuffle anything because the data is already in there. Okay, I actually wanted to talk about something else in the meantime, so this is why I rewind. As a reminder regarding terminology for transformation, stage, task, job can be daunting, right? All of these terms. So the way to look at it is that the job is the full, when you trigger an action, that triggers a job, right? A job is basically a sequence of stages, right? Stage 1, stage 2, stage 3, stage 4, that gives you a job, right? And then within a stage, you might have multiple transformations. That is what we saw here. Stage is made of multiple transformations, right? And then something happens, but here it's on the physical level. It's not logical. On the physical level, you split the stage into tasks, right? So this is how a stage can both be seen as consisting of many tasks, or it can be seen as consisting of many transformations. It depends if you look at the logical or at the physical level. Okay. So now this is my battery issue that I might have to swap for the other one over there. There you go. So here, let me ask you a question. So imagine that we have this dependency graph. These are all the RDDs that we created. It looks like this. And then I would like to request the data corresponding to this RDD over here. For example, because I want to see it on my screen, or because I want to write it back to HDFS. So I'm going to pull the trigger here, and it's lazy. So suddenly all the cluster comes into motion, everything gets computed stage after stage, and then at the end, it writes everything down to HDFS. Then you pull the trigger right here on this different RDD. Now you want to print that to the screen. So you pull again, all the computations are basically triggered all over the cluster, all of that is computed, and you find this on your screen. Then you decide to have yet another job, yet another action. You pull the trigger right here, and you want this, for example, to be counted. You want the count of everything, so that triggers all the computations right here. Now, two questions. First, do you see anything inefficient here? And second, what can we do about it? Yes, the microphone. Where is the microphone? Oh, here. Yeah. Let me.
There's a bottleneck.
There is a bottleneck, yes.
So probably if we have to wait every time for the process to finish, it will be very slow. So maybe we could parallelize processes if it's possible, or we could engineer it differently, the architecture.
Yes, so the bottleneck, you are right. This here in the middle is obviously a bottleneck because there is an RDD that is common to all three. Regarding the architecture, yes, we would like to adapt something in the architecture to make it more efficient, right? Now, what I would like to discuss is what we mean exactly with this bottleneck. Because technically, when you look at this, if it were only for one action, just this one, for example, and you don't care about the others, you do it just once. Basically, if you just do this, the bottleneck is not a problem, right? Because all you get when you take everything that's up there, you turn it into action stages, you have the sequence of stages, you execute the stages, you get the results, right? The fact that it's organized that way is inherent to the query that you're executing, right? That's the plan that you put there. So you are right that, if I correctly understood you, that the user could change the way that this is organized. Maybe there are more efficient ways of doing that, right? So this is one thing that we could have, is that the user builds a different graph so that it's a bit more efficient. But imagine that you cannot change the graph. This is what you have. It has to be this way. And you want to do these three computations right here. What can you use to your advantage, basically, that it's a bottleneck? Anybody else? Yes, over there? Right, but you're right. This is exactly this bottleneck in the middle is exactly the center of attention. Yes.
Well, since the logical architecture is not from the queries is not changing, I can just store the result of the bottleneck and then use it or pre-compute it for the other queries.
Yes. So basically, you can tell me if this is what you have in mind. Basically, you trigger the computation and keep stored on that where the bottleneck is, you keep that stored. And when you re-trigger, you don't recompute what's above, you reuse what the intermediate results that you've stored there, right? Exactly. Who sees it? All right. In fact, this is why it's called resilient distributed data sets, because of that sort of things. So the idea is that when you write the Python code to create that graph structure with your intermediate computations, you can also, in Python or whatever language you're using, pin that RDD. You can pin it in the sense of telling Spark, please keep that in memory. Do not throw away these intermediate results. Keep them in memory. Maybe put them on disk. If there's not enough memory, you can even ask memory, disk, you can say what your preference is. But you're basically pinning that RDD here. That's why I put these black lines here, to basically keep it there. And that way, all of that does not need to be recomputed because you keep in memory these intermediate results, right? And then when you trigger the action, only this needs to actually be computed. Who understands? All right, on Zoom too? Checking that nobody is actually sleeping on Zoom. Raise your hands on Zoom if you're following. Okay, yes, very good. Good, perfect. Another reason why it's called resilient is that it might not always work. For example, if you ask Spark to pin too many RDDs and there's not enough memory, it might actually have to really throw some of them away. It needs to prioritize, basically. You can have priority. But if that happens, it's not a problem. The worst that can happen is that it's going to recompute. That's the worst that can happen. So it's going to be slower, but you're not actually failing the whole job. All right. Okay. So again, regarding the partitioning, this is the spaghetti that I told you again about. It's when every piece of data in the output depends on a lot of data in the input all over the place. This is where you need to shuffle the data around in the cluster. And if it turns out that the input data is already partitioned and distributed the right way, then you don't need to shuffle around, right? So, for example, if you want to aggregate based on the birth dates and the data is already grouped by birth dates in the way it's located on the machines, then you don't need the shuffling. And so this is the cases where you can let go of some of the spaghetti in here. Okay. Okay, so this concludes the optimizations, and most of that was actually just a reminder of what we've done in the previous weeks. So now let's move to new material. So we are going to discuss now data frames. Who already heard data frames? Who already heard data frames before the validation lecture? Okay, some of you. Pandas, right? You heard of pandas. So we are going to connect now this all together, basically the pandas library in Python, with the validation of JSON, because we saw that when you have a collection of valid JSON data, you can nicely draw a visual that we call a data frame. And it turns out that we also have the data frames in Spark. So we have RDDs, right, that are collections of whatever, and transformations that turn a collection of whatever into another collection of whatever. One way to do that, in that case, it's a map transformation that has a function that maps every input value to one output value. And when you write the code in Python, it can look like this. Well, if you have a simple use case, that's kind of okay, right? You can just write a few lines of code and it can be quick. But what I would like you to see, and hopefully the exercises are going to help, is that as soon as your query becomes more complex, the code here is going to be more and more difficult to write. It's going to be incredibly complex, even to a point that a human can no longer do it. And this is kind of the problem that we would like to solve. You basically need to see that this code, in fact, is what we would consider low-level code from the perspective of a database system. This is something that normally we would not like the user to have to do. Because we have something better, we have high-level languages like SQL that is much easier to write, more general, and it's easy to optimize. So this is the direction in which we are going now. This here is a simple use case where you just deal with strings, right? So you basically, for RDD2, you filter the strings that contain Spark. Then you map to the number of items that are in there. Then you reduce by key, whatever it does, right? But even the fact that it's complicated to figure out what it does already tells us that something's wrong. But even worse is when you deal with JSON, Spark doesn't know JSON. To Spark, JSON is just a whatever that you can have in the RDD, but it doesn't know about it. So if you have an RDD of JSON objects, which you can have, because you can have RDDs of whatever, if you have RDDs of JSON objects, from the perspective of Python, a JSON object is a dict, right? It's a dict data type. So if you want to deal with JSON, that's fine, but you have to do it with the Python methods to handle dicts, right? It's all Python code that deals with JSON. And then what you end up with is that you have to put these Python codes that deals with JSON inside of your functions. Remember the lambdas, inside of the functions, you have to put all of that codes that is supposed to deal with the Python dicts, which is the way to deal with JSON objects, right? And again, for a human being, this is not easy to read. It's really not easy to figure out what that does, even less so to write that code. So there is a solution that was actually put in place by the engineers of Spark. It was not there in the first version of Spark. It's something that was added later because they acknowledged that there was a problem with the complexity of of the code when you deal with collections of objects. And the idea that they had is that if RDDs are collections of whatever, then what if we make that whatever a record or a row or an object, right? So if you have a collection of rows, what is a collection of rows? If the rows all have the same attributes and types, what is that? A collection of rows? On Zoom? What is a collection of rows? Yes, yes, I see an answer here, a table. This is indeed a table, right? So if every one of these values in your collection is a row and they have the same attributes and the same types, then the entire RDD would correspond to a table, a relational table. Do you see where we are going? If we are able, in some cases, to deal with the fact that the values are rows and the RDD is in fact a table, why don't we use SQL? Because SQL is the best way to deal with tables, right? Select from where and so on. It's very easy. So this is the whole idea. In the particular case that the records, the values in the RDDs would be rows, the entire RDD would be like a table, and then we can use SQL. But there's even something better than that. It's that the way we store these tables on the cluster, on the machines, is extremely efficient. And the reason why it's extremely efficient is that it's going to be stored in the memory of the machines column by column, rather than row by row. And if you store it column by column, remember that since it's a relational table, in the same column, we have the same type. So for example, what we have here is integers all over the place. It's a list of integers. Here, maybe it's a list of dates. Maybe here it's a list of booleans. Here it's a list of strings, right? So since it's very homogeneous, then we can optimize the storage because storing a sequence of integers of all 32 bits is extremely efficient, right? And something else that happens when you store the columns in that way is that you do not need to repeat the name of the column. Remember that when you have a collection of JSON objects, like in the JSON lines data set, you have to repeat the keys in every one of the objects. Do you remember that? The keys has to appear in every single JSON object, even if it's the same keys all over the place. This is the reason why we saw that we can turn it into a data frame after validating it and then save it as Parquet, right? It's the same idea here. If it's all integers and they are stored together and it's the same column, we no longer need to store the name of the column every time. We just store the sequence of integers. This is something that we know how to do. So the concrete benefit of that, it's very simple to understand. The memory that it takes to store data in the form of data frames is much more efficient. It takes less memory. If you had to store the same thing as a collection of JSON objects in Spark, as an RDD of JSON object, it would take a lot of memory. But the moment you turn it into a data frame, it's going to consume less memory, right? Now, just to be extremely clear, because I made an additional jump in here, this is a relational table in the particular case that we have a relational schema and it's flat, right? So if the rows are flat, we have a relational table. You remember from the validation week where we studied validation of JSON, that if you have a collection of valid JSON objects, then you get a what do you get when you get when you have a valid collection of JSON objects? On Zoom, I know you know. Collection of valid JSON objects is a starts with a D. Sorry? Yes, you could. In fact, when we study document store, we see that we can call the objects documents. But in the particular case that the documents are all valid against the same schema, what do you get then? The entire collection would be a A data frame, yes, exactly. So in the flat case, the rows give you a table. And in the case that it's not flat, but it's still valid JSON, then you get a data frame, all right? And in the case that you have data frames, which are a generalization of tables, then you need less space. Now, this is where it becomes beautiful. Because then, inside your code, you no longer need to write all of this code with the flat map and filter and the lambdas and the Python code that deals with JSON. Instead, you can just replace that whole thing with a SQL query. So you see now why the brush up that we did at the beginning of the semester was useful, why it was worth looking into SQL again. Because then you can just write select from where, you know the clauses, right? Select from where, group by, having, order by, limit, offsets, right? And in fact, for a human being, it's much more intuitive to write a select from where query in SQL than it is to write Python code. In fact, it is so popular that even business people or people outside very far away from technical aspects, they can also write SQL. They can also learn the SQL language. So the good news is that in the particular case that the RDDs are valid JSON objects and can be seen as a data frame, we gain in memory because it takes less space to store the data in memory. And we gain in productivity because we can use SQL instead of writing a list of Python transformations. Who understands that? All right. So this is great news because you already know SQL. So now all you need to do is actually use that. So that you'll have at the exam, by the way. You'll have PostgreSQL database with data in there, and you'll be asked to write SQL queries. And you'll also have JSON data sets that are valid, and you will also be asked to write Spark SQL queries, right? We call it Spark SQL. Technically, call it the SQL of PostgreSQL, and the SQL of Spark is a little bit like the difference between Zurich Dutch, Basel Dutch, Bern Dutch, Walliser Dutch. It's the same thing. These are just dialects of the same language, right? But they are really not so different from each other. Okay, so this is the thing. And by the way, in the Jupyter notebook, you will not even have to write this spark.sql with the string and so on. In the Jupyter notebook, you just put the SQL and that's it. In the entire cell, just the SQL. So it's really made in such a way that it's easy to use. All right, so how do you use it then? Well, your data might be a CSV file, it can be a JSON lines file, it can have various formats, but Spark is smart enough to turn these into data frames because it can auto-detect that there is some homogeneity and some schema. For example, if you input that data here, dataset.csv, as a human being, you see it immediately, right? As a human being, you see it's always an integer and then a comma and then a Boolean, right? Spark, in fact, can detect that. And what it's going to do is it's going to create a data frame where the first column is an integer and the second column is a Boolean, right? And the names of the columns are, of course, taken from the first line in the CSV file. Who understands this? Right? Okay, so here we turn a CSV into a data frame. If we did not have data frames, the only thing we could have done is open it as a text file and have an RDD of lines, an RDD of strings, right? That wouldn't have been very convenient. But since now we can directly open it as a data frame, then we can use SQL in order to work on that data frame. Note that this particular data frame happens to be a table because here it's flat, right? But in general, it doesn't need to be flat. CSV will be flat, but JSON will not necessarily be flat. Now we have the same in JSON, foo, blah, 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 bar, and then the Boolean. You see that you can build a schema against JSON. You can see that foo is an integer and bar is a Boolean. So you want objects with two keys, foo and bar. Foo is an integer, bar is a Boolean. Then you can turn it into a data frame. You don't even need to supply the schema or build any schema here because there is an automatic detection. Spark will figure it out for you. Just give the data and Spark will figure out that you have an integer and a Boolean column. All right. And it even works if the data is nested, if you have arrays on objects and so on, as long as it's homogeneous and the objects all look alike, then Spark is automatically going to build a data frame. Now, I love SQL. A lot of people love SQL. A lot of people find SQL much easier to write. but there are also people who are big fans of what is called data frame APIs. So there are people who don't want to write SQL. They prefer to have fun with chains of transformations. Well, if that's your case, then don't worry, because you can also, instead of SQL, write a chain of transformations like this. You just need to be aware that it's not the same list, right? There's the transformations on RDDs. Here it's transformations on data frames, right? There's also a whole restaurant menu of them. I'm not going to drive you through them. So at the exam, you will have a choice. I strongly encourage you to use Spark SQL because it's much easier to learn, and also it looks like Postgres SQL. But if you really, really want to have to use the data frame API, then of course you can do it. And if you can solve the same questions, then that's totally fine with me. Okay. Who prefers this? It's okay, right? Who prefers SQL? I see more hands raised, right? Okay. All right. Now, do you remember in the lecture on validation, I gave you a 101 on data types. What I told you back then is that there are many, many different technologies for schema validation, for formats, and so on. And every technology will have a list of types, right? Specification of the types available. You have types in Java, you have types in Python, you have types in XML schema, you have types in JSON schema, you have types in Parquet. Well, you also have types in Spark SQL. But remember what I told you. Even though it's going to be different lists of types, on the high level, if you zoom out and take a bit of distance, it's really always the same story. The types almost always look the same. The names might be different. There might be a few differences here and there. Some of them might not support some types. Some of them might have additional types, but it's always the same. Well, here, this is the list of the ones you have in Spark. For Spark data frames, the types you can have in the columns. Normally, at least if I did my job correctly a few weeks ago when I told you about the types, if you look at this, you should be comfortable because there shouldn't be any surprise there, right? That should feel familiar. For whom does that feel familiar? Okay, perfect. For those of you for which it doesn't, don't worry, because I have yet another correspondence table where I have Java types, I have Python types, I have JSONic types. These are the same as for JSON and XML schema. And there is the whole correspondence. So you see, the only difference really is the way they are called, but the kind of types are always the same. Byte short, integer, long, these are for the fixed number of bits integers, right? 64 bits, for example, for long. Then you have float and double. This is for floating point numbers, right? On 32 bits or 64 bits. Then you have Booleans, you have strings, you have decimal numbers. You have timestamps, dates, binary even, and so on. So no surprise here. The names might be new, but it's really just yet another list of types that looks just the same as other lists of types in other technologies. For whom is that intuitive? This correspondence table, right? Okay. Very good. And by the way, the correspondence with Python is actually important because when you try to use the transformations or, get some of the data in Python, it will actually convert back and forth between data frame types and Python types. So the correspondence is actually important. All right. And for people who use Java instead, then of course it's going to convert to Java types. Okay. So these were the atomic types, right? The ones that are at the leaves of the tree. And then we have the complex types. But here there shouldn't be any surprise. We have arrays and objects, right? Arrays are called array types, and objects are called struct types in data frames, right? And again, in Python, that would be a list for the array type. But, and here, this is where you have to, basically, it's like going to Valley-sur-Duche, right? It's slightly different. So if you look at the map type, what is a map type? Well, technically, it's also an object, right? Just like the struct type, it's also an object. The difference between the two is that in a map type, all of the values in your object have the same types. That's the difference with a struct. In a struct, you can have a key that is associated with a date, another key that is associated with a string. This is typically what you are used to in data frames. But you can also have map types the way it's mapped to Python can differ. Technically, you could also map a struct type to a dict in Python without any problem, but it can also be done as a list or as a tuple. I have no idea why. Personally, I would have used a dict rather than a tuple. Anyway, you see, we have this correspondence between the languages. And we have objects and arrays. They are just called arrays and structs in data frames. All right, map type you actually don't see very often. I think it's something that is a bit rarer to use objects in this way. Okay, now, how do you read the data? I already told you it automatically infers the schema. Well, this is how the syntax looks like. You have this spark.read. And then your format. So Spark read JSON, Spark read Parquet, Spark read CSV, text. So then you just put the path to your cloud. So it could be HDFS, could be S3, could be Google Cloud, could be Azure. And this is where it's automatically inferring the schema and creating data frames, right? So it doesn't matter if you have JSON, Parquet, CSV, it will infer a schema. Text, maybe do not push it. Text, it will just create a single column with of type string, right? What is JDBC? Well, that is a connection to PostgreSQL, because you can, in fact, connect Spark to PostgreSQL and open a PostgreSQL table as a data frame, and then apply Spark transformations on it. So you see how modular it is. You can connect anything to anything. You can use Spark with S3, with HDFS, with Google, with Azure, with PostgreSQL, with your local drive, and so on and so on. Avro in there, I'm not sure if I mentioned, but that's another format. Whenever you add new formats, basically it's not going to be directly in here after the reads. You just have to put it in a string in there. This is for all the formats that are not known in advance, like the not a built-in format. And then it just depends on what you install on your machine. You can just install support for more formats, and then you can use them. All right. So this is how you create data frames from data sitting in your data lake, in your cloud storage, and Spark is going to turn them into data frames. By the way, in one of these cases, well, in two of these cases, there is no need to infer a schema because the schema is already here. Can you see the two that I mean? I don't include Avro because Avro we didn't discuss. But if you look at the other 5, in 3 cases, you cannot infer really any schema. In 2 cases, you can infer a schema. You already have a schema, I mean, in 2 cases. What are the 2 cases in which you already have a schema? You just need to read it. What do we have here? Yes, correct answer.
Yeah, so in the Zoom, Parquet and Postgres.
Yes, exactly. Indeed. Remember that Parquet is a binary format that directly stores data frames. So it means that in that Parquet file right here, there is already a schema in there. So it means that this here is going to be super fast because it doesn't need to infer the schema, it already has it. It will directly read the schema, it already knows the structure of the data frame and populates it with data. Here, it's slower because there is no schema. It needs to go through the entire data and scan through it in order to infer the schema. Same here in CSV. Same here, where it's just going to take a string. And JDBC is the same, there is already a schema. You know that in a relational database system, all tables must have a schema. And so we just take that same schema in order to create our data frame. Who agrees with that? Okay. Parquet, Postgres already have a schema. Avro also has one too, but again, we didn't discuss Avro so far. Okay. So you see, this is why it was so useful to actually have this brush up on Spark SQL, because now you can just go ahead and use it. All right. So what's going to happen now is that if you do use data frames and you do use Spark SQL, Spark will do a lot of things automatically for you. It's in fact going to kind of convert the data frames to RDDs in an optimized way, but you don't even need to worry about them or even see them, right? Physically, it's going to actually use RDDs in the back. Your plan, so technically when you write Spark SQL, is going to be transformed to something like this, which is technically a query plan, right? This chain of transformations. and it's automatically going to be transformed to RDD transformations. But the nice thing is that all of that here is hidden from you. You don't even need to worry or even understand how this is done. It's going to be optimized in the best possible way so that the execution is fast. So this is an illustration from the paper when they presented it. There is a whole pipeline of fancy tools that are able to optimize and make it faster, right? This is advanced here. You don't need to go into the details of that. All you need to see is that on the very left, you have your data frame and your SQL query. That you understand, right? What a data frame is and the SQL query. And it goes through that pipeline of complex things that nobody understands. And at the end, it spits out some RDDs, right? So it's all the magic that happens to basically make the SQL execution against data frames super fast. Now, not surprisingly, this is how Spark SQL looks like, right? When you look at it, shouldn't surprise you. That corresponds to the blush up. Select from where, group by, having, order by, limit, offset. It's not all mandatory, right? You can also have only a subset of these, but this is the whole list. It has to be exactly in that order. You cannot put the having at some other place or put the limit at some other place. It has to be in exactly that order. Who is comfortable with that syntax by now, right? We had the brush up, very good. We had the brush up at the beginning of the semester. Now, if you look at that specific query and imagine the data flow in the query, can anybody tell me what in this query is spaghetti and is going to cause shuffling? Do you see these parts of the queries that are going to cause shuffling? Maybe the where? Does the where cause shuffling? Maybe the group by? What is it that causes shuffling? Who thinks that the where clause is going to cause shuffling? The where clause is going to be a filter, right? Remember, the best way to implement a where clause is to filter out the data and to just keep the data that satisfies the criterion. A filter is a narrow transformation. There is no spaghetti in a filter, so indeed there is no shuffling. But do you see other places where there is going to be shuffling? Yes, over there we have. Yes, bingo. Group by and order by. Exactly. This is what causes the shuffling. Right? A group by, because you need to put the data that is in the same group together. So you're going to shuffle around the data so that the data in the same group is located together. The same for the order by. The order by shuffles the data. Well, that's what an order does, right? When you reorder the data, you obviously have to shuffle the data. I mean, if you play poker and you have to sort the card deck, then obviously you need to shuffle the card. Even though shuffle is used meaning randomness in the case of cards. Here, shuffling really just means you move the data around. So very good. Group by and order by. Here's my next question to you. Do you think that shuffling will happen twice? Or do you think this is a case where we don't need to actually shuffle every time? Who thinks shuffling will happen twice? Don't see any raised hands. Who thinks shuffling will happen only once? I see a lot of raised hands. Why? On Zoom, people are less shy on Zoom usually. Writing down is kind of easier. Nobody on Zoom? Why does the second shuffling not need to happen? Time to write down. Yes, what can you read maybe?
Because the country could already be ordered during the first one.
Yes, exactly. You see, what we group by and what we order by is the same thing. So when you do the group by, you're going to put the data together all by country. So Switzerland will be together, Germany will be together, China will be together, and so on. So at that point, it's all partitioned by country. The halving is like a filter. It's just like the where, but after the grouping. So this doesn't shuffle. And now you order by country. But that's great. The data is already organized by country, right? So you don't need to shuffle again. The data is already where it needs to be. Who sees that? I know you do. There was a lot of raised hands earlier, right? Okay. So this actually does not require a second shuffling. That is one of the cases that I call pre-partitioning. If the data is already partitioned in such a way that the data is already where it needs to be, then you don't need to shuffle. That is an optimization, right? You could still shuffle if you want, but that would be useless. That's what I'm saying. Yes?
The question. So what if the attribute is not the same?
If the attribute is not the same, then you need to shuffle again, right? That's basically what happens. Yes?
What if we order by, for example, ascending or in a different way than we did in the group by? Would we still just change the group ordering and then it's still not a shuffle?
Exactly. It doesn't matter if it's ascending or descending because it's already where it needs to be, right? You just need to keep track of where it is. Yeah. Mm-hmm. Okay. All right. I'm almost done. Now, I think we need a break, actually. So it's 9. I just have a few slides left. What I want to do is show you the limits of data frames and SQL. I will break it to show you that it doesn't cover all cases. But that I will do in a quarter of an hour. So I'll see you at 2 minutes at 17 past 9 for the continuation. Thank you.